Okay, so we are going to take a recap of what we have studied in proportional logic so far. So we started with the definition of propositions. The propositions are declarative statements that are true or false. Right? We can assign true or false values to these statements unambiguously. Then they are called propositions. Then we looked at the syntax of propositional logic. So the alphabet of propositional logic consists of all the atomic propositions which can be countably infinite in number. Like P denotes this set, which is P0, P1, P2, etc. These are allowed letters in our alphabet, and then we have 5 connectives: one unary connective, negation, then implication, bidirectional, conjunction, and disjunction. These are 5 connectives. Then we have the left parenthesis and the right parenthesis. So these are the allowed symbols in our propositional logic formulas. So this is the syntax. So in the language we only have these things coming. Okay. So now when you have this atomic propositions, let's say P, we want to create the formulas, the collection of all good formulas or well-formed formulas in the propositional logic, which we denote by capital Phi. And how do we construct that? So if P and Q are in phi, then negation P is in phi within brackets. P or Q within brackets is in phi, within parentheses P and Q is in phi. P implies Q, P if and only if Q. All these things are in phi. So first all the atomic positions are in phi, right? And then we can apply this to generate more formulas. So whenever you have two formulae, you can apply these operations and then we get more formulae, and these are all well-formed formulae as far as we write in precisely this form according to these rules. So these are all these are called well-formed formulae or the formulas in propositional logic. Okay. Then we looked at the structural induction principle, which states that suppose you have a universe U, a base set B which is a subset of U, and a collection of functions which takes elements of U or pairs of tuples of elements of U to elements of U, which denote by F. Then P is some property that is satisfied by B. If you want to show P is true for all elements of the smallest inductive set C of U B F, then we can use structural induction, right? So that is what we studied there. We also looked at construction sequence, and then we saw that the the last elements in the construction sequences, right? The collection of such things is a set, and that is also the smallest inductive set. So we saw that. Then we looked at an algorithm to check for the well-formed formulae given a string is a well-formed formulae in our language or not. Then we studied the semantics. In the semantics, the first thing that we look at is valuation or assignment, which is basically a map from the atomic formulae to the Boolean variables true and false. And then we can generalize this to arbitrary formulae by the following rules: that valuation of negation alpha is defined to be true if valuation of alpha is false, and if it is valuation of alpha is true, then the valuation of negation alpha is false. And then we said that valuation of alpha disjunction beta is false if both alpha and beta are false under V, and if at least one of them is true, then this is also true. So that is the, and then we basically define other connectives in terms of these two connectives. So therefore alpha and beta is defined to be negation of negation alpha or negation beta, alpha implies beta is negation alpha or beta, and alpha if and only beta is alpha implies beta and beta implies alpha. We also looked at truth tables. We looked at tautologies. What are tautologies? The well-formed formulae which are always true under every valuation. Then contradictions are those formulae which is never true under any valuation. Then we looked at satisfiability, that if a formula can be made true by some assignment, then it's satisfiable. So we looked at these notions: validity, satisfiability, consequence, and then related questions. A given formula, whether it is valid or satisfiable or consequence of a collection of formulae or not. So these are the important problems that we looked at. And then we looked at the unique readability of well-formed formula, that there's only one way to parse it and understand it. We also saw that without parentheses we can write well-formed formula without confusion. The Polish notation is a way to write this formula without confusion and without brackets. Then we looked at models of formulae, that so that the model is basically an assignment which makes the formula satisfied. Then we said we looked at tautologies. I say tautology alpha, writing this way by which means that alpha is always true under every valuation. And if I say V and this symbol and F, that means that the collection of formulae in F are all made true by this valuation. And similarly, when I say F, G is a consequence of F, we say that whatever valuations that makes F, the elements in or formulas in F to be true, must also make G to be true. We also looked at axiom systems and formal proof and derivability. Axiom systems AX and H, we have looked at the Hilbert systems. So these are all parts of Hilbert systems, but different models. And then we looked at derivation, right? So derivation of a formula. I say that alpha is derivable, or alpha is a theorem, or alpha is a thesis, or alpha is provable if you can find a sequence, right, of formulae starting from the instances of axioms in AX, right, and then use mod exponents, and then we can use this in a finite sequence and then arrive at alpha. Then alpha is derivable, right. Then we look at a logical equivalence. Say two formulas are logically equivalent if every valuation that makes one of them true also makes the other one true. Then we looked at derived rules, which are very important in writing simplified proofs, because from the system alone, right, if you want to prove, then the length of the proof will be generally very high. So we will derive several rules and say that okay, these are all rules which are sound, and therefore we can use it as a shortcut to make the proof simpler and shorter. So one of the most important rule is the deduction rule, which says that if I want to prove alpha implies beta from a collection of formulas F, then it is also good enough to prove that F union alpha proves beta. So if F union alpha proves beta, then it is equivalent to saying that F proves alpha implies beta. We showed that the deduction rule is sound in the sense that if I have this F union alpha implies beta is valid, I mean, then I can give a proof of F proves alpha implies beta without using the deduction rule, right? So there you can find a proof in the system AX itself. So therefore we can use it as a shortcut. Then we looked at consistency, right? We say that a formula is consistent if alpha is consistent if negation alpha has no proof in the system. Okay? So if it is not derivable, then it is consistent. If negation alpha is not derivable, then alpha is consistent. And if you have finite set of formula alpha 1 to alpha n, then they are consistent if the negation of the conjunction of these formulas is not provable. Then for arbitrary set we said that if a very finite subset is consistent, then it is also consistent. That is our definition. Then we said maximal consistent set, that set is maximal consistent set if it is consistent, and if I add anything outside this x, then it is not consistent. Every formula which is outside x, it is not consistent. We looked at some interesting results of and properties of this, and one of the interesting result is Lindenbaum's lemma, which says that any consistent set can be extended to a maximal consistent set. Then we looked at soundness of propositional logic, right? Soundness says that if I can prove a formula, then it is a tautology, right? So in the system, if I prove a formula, then it is always true. It's valid. So theorem beta means that tautology beta. That is the soundness. We also want to prove the other direction, the completeness, that we can actually prove every valid statement, right? So that we will prove, but for that we need Henkin's lemma, which says that if beta is a consistent well-formed formula, then beta is satisfiable. And once we prove this Henkin's lemma, then we can show completeness that if beta is a tautology, then beta is also derivable. Then we proved what is called Koenig's lemma, right? Koenig's lemma is a result on trees. So if you have an infinite tree on which has only finite degrees, that every vertex has at most finite many neighbors, then it must have an infinite path, and then we used it to prove finite satisfiability. So what is finite satisfiability? It says that X is satisfiable if and only if every finite subset is satisfiable. Using finite satisfiability, we proved compactness, which says that if alpha is a consequence of a formula set of formula X, if and only if alpha is a consequence of every finite subset Y of X. Okay? This is called compactness. From compactness and reduction lemma, we can prove strong completeness, which says that if alpha is a consequence of X, X is some arbitrary collection of formulae, if and only if alpha is provable from X in the system AX. Okay? So this is the strong completeness. So the difference is that, like here we don't have any assumptions apart from the instances of axioms, right? But here X is a set of any collection of formula, right? So X is any some arbitrary collection. If I can show that alpha is a consequence of arbitrary collection, then alpha is also derivable from that set. Then finally we looked at the conjunctive normal forms and closal forms, and then we looked at resolution. Right? Resolution is the thing that we looked at finally, which is a method which is sound and complete, which can be used to verify the or check the satisfiability of a well-formed formula. Right? So these are the things that we studied, and I want you to go through this carefully, look at each of these and solve all kind of problems that you can come up with. And I will give some problems here, but you also look at many more problems, and then once you are thorough with this, we can start the first order logic. Okay. So here are the some questions. So here I introduce a new setting, that sigma is a set of binary strings of finite length. Okay. Sigma can be infinite, but every binary string is of finite length. Okay. Some example like sigma is 0 0 1 0 1 1 1 1 1 0 1 0 1 1 or 0 0 1 0 1. So these strings are there in sigma, for example. And then once you have once you fix a sigma, consider the following game. Okay, so the game has the following rules. Rule 1 says that you can write down any string small sigma in sigma. Okay, so whatever is there in the given set, I can immediately write it down. Right, that is the first rule. Now, suppose I have already written down a string, let us say sigma. Then I can write sigma followed by a 0 and sigma followed by a 1. Right, these things I can write down, either one or both I can write. Okay, if I write sigma, then I can write sigma 0 and sigma 1. The rule 3 says that if for some string sigma, both sigma 0 and sigma 1 have already been appeared, in your writing, then you can write down sigma. Okay, suppose I have already written down 0 0 and 0 1, then I can write down 0. Okay. These rules can be applied a finitely many number of times. Okay, you can only apply each rule a finitely number of time to obtain some string. So these are the 3 rules in the game. Okay, now the question is, suppose I give you some set sigma, right, of strings and an arbitrary binary string, let's say t. Question is to check whether t can be written down at some point in time, right? In finite number of steps, I can actually write down t or not. Okay. Now I say that sigma then let's say proves t if t can be written down following the game rules. Okay. So t can be derived from sigma if t can be written down following the game rules starting from sigma. Okay. Now it should be already familiar to you, like to the things that we have already looked at, right? Basically, this is imitating a kind of proof, right? So how we write down proofs. Okay. Now we can ask questions on this. For example, suppose I have the sigma to be given as set 0 0 and 0 1. It's very easy to see that 0 0 1 0 0 is something that you can write down from this, right? Because if I write down 0 0, I can write down 0 0 followed by 1. Since I have written down 0 0 1, I can write 0 0 1 0. Then I can write 0 0 1 0 0, right? So show that this is something that you can try to work out. Show that any string starting with 0 can be written down from the given set, 0 0 and 0 1. Okay, any string of finite length can be written down from this. Then I want you to show that you cannot write down 1 from this set. Okay, you can never write down. So 1 is not derivable in this system. Okay, so generally, derivability is like one, to show something is derivable is easier because you can actually find the construction sequence and write it down. But then to show that it is not derivable is something much more difficult. But again, you can try to prove this. So give an argument why one cannot be written down. Okay. So or in other words, you can write if 0 0 and 0 1 derives a string t, then t must start with a 0. Right? It's equivalent. Therefore, one cannot be written down. Prove the following theorem. Okay. So suppose sigma is again a collection of finitely many. I mean, an arbitrary collection of finite strings of zeros and ones, binary strings, and t is derivable from sigma. Then there is a finite subset of sigma, let's say sigma dash, such that sigma dash proves t. Okay, this is similar to our finite satisfiability and things like that we have proved, right? So try to prove this, and then fourth question is to show that the set of formula A implies B, not A implies not B, and A or B or C can be used to derive not C implies A. Okay. Fifth question is write a formula using only disjunction and negation to express the symbol XOR, P XOR Q. Then next question, give 3 examples each of well-formed formulae that are tautology, formulas, 3 formulas that are satisfiable but not a tautology, and 3 formulas which are contradictions, that is not satisfiable. Now suppose gamma is a collection of formulae and alpha is a consequence of gamma. Show that if this happens if and only if gamma union negation alpha is not satisfiable. Okay, I think we have already done something very similar to this, or maybe even this, I don't know. but try to look at this. Now here is an interesting question. You have already probably heard about the n queens problem. That is that you have an n by n cross n chessboard and you want to keep n queens on this board such that no two queens attack each other. So queens attack each other if they happen to be on the same row or same column or same diagonal, any small diagonal or large diagonal, whatever diagonal it is. Okay. So I want you to express the four queens problem as a well-formed formula, right? That queens are sitting on this 4 by 4 board without attacking each other, right? Four of them are there without attacking each other. So that defines the four queens problem. So I want to try to find a well-formed formula for this. Then ninth question is to check the given formula is valid or satisfiable or unsatisfiable. Right? So here I have written down two of them. You can try to look at more, write down something and then see what happens in that case. And then 10th question is to show that the following are equivalent. Right? Alpha 1, alpha 2, alpha 3, etc. Alpha n is given. Then beta is a consequence of this. Or I can write down alpha 1 implies alpha 2 implies something, right? Alpha 3 implies something, etc. Alpha n implies beta. So this, I think we have already looked at these things before in the proof of strong completeness somewhere, but I want you to formally write down the equivalence of these things. And finally, like that is also equivalent to the conjunction of alpha 1 to alpha n implies beta. Right? These are all equivalent statements. And finally, let's say alpha beta are well-formed formulae, then is the following correct? Okay, if alpha implies beta, then alpha implies negation beta. If yes, argue why. If not, justify with examples. Okay, I think that's it. So now I want you to go through this very carefully and thoroughly and solve these things. You don't have to submit these questions unless if you have some doubts, you can ask me, of course, or discuss with your friends. But by next week, I want you to be very clear about what we have covered so far and all these topics, and several questions you must have worked out. Okay, so all the best, and see you next week with first order logic.